20. And what we will discuss is nuclear chemistry. This is a list of the topics. And this is a short video that you can watch at home that highlights the relevance of the stuff that we cover in class. So it's just to remind you that the things that we discuss, even though sometimes there seems to be a little bit too off there and not really applicable, they are very applicable. Okay, so watch that video if you get a chance. It's just like 2 minutes long. And as I mentioned in class, we don't talk much about the history of chemistry or science in this class, but it helps you understand where all of our knowledge comes from and where our way of thinking comes from. So if you look at the discovery of radioactivity, it's quite interesting because back 100 years ago, they knew that some substances could absorb light. When they were exposed to light, they would absorb energy. And then when they were taken into a dark room, they would glow in the dark. That is, they would emit that energy that they had absorbed. And that's a phenomenon that we call fluorescence. However, Becquerel noticed that some minerals that he had in his laboratory, when he put them in a drawer with photographic material, photographic film, and he came back a few days later, the photographic film had been developed. It had stains that were only possible if the material had emitted light. But again, that material had not been exposed to light previously. So where was that energy coming from? That was one of the big questions. How come that a substance by itself is emitting energy, light, without having to react with something else? A few years later, Rutherford noticed that certain type of nitrogen atoms could be converted into oxygen when he bombarded them with alpha particles. This was revelatory because what they knew from Dalton's theory, atomic theory, and one of the things that he says is that atoms of one element cannot be converted into atoms of a different element. So in chemical reactions, Dalton said, the atoms are rearranged, but they are not transmutated. They are not transformed into something different. As we mentioned, Dalton himself, he was an alchemist, but he would have had trouble believing what Rutherford observed. So we have this big question again, how does this happen? What is causing this behavior? And one of the fundamental observations and fundamental reasons why they didn't think that was actually possible, transmutation, was because what had to change to take an atom of an element and convert that into a different element was the nucleus. And chemical reactions, we know, deal with changes in the electron cloud, in the electrons around the nucleus. So what do we know about the nucleus? And this is to remind you actually that the knowledge that we gain in our science courses, the most important part of that knowledge is what we can remember, recall, understand like 2 years, 3 years down the road. So that's why we don't memorize things for the exam, but we try to gather this broad understanding of science. So when you think of an atom, what do you know about it? What is that mental model, mental representation you have in your heads of an atom? And where is the nucleus in that atom? So we know that the nucleus is extremely small compared to the atom itself, which is already extremely small, and that most of the matter of the nucleus resides, of the atom resides in that nucleus, which makes the nucleus extremely dense. The composition, we have electrons around the nucleus in the electron cloud, and we have protons and neutrons in the nucleus. Yes, we know that there are other subatomic particles, but for the model that we use in this class, we will only consider neutrons, protons, and electrons. So that's what we call the three-particle model for the atom. Z would be the atomic number, that is the number of protons in an element, in an atom of an element, and we know the number of electrons is going to be the same because atoms are neutral. A would be the atomic mass, which is the mass that you get when you combine the number of protons and number of neutrons, which are the two subatomic particles that have significant mass. The mass of the electron is negligible. And when we subtract A, or when we subtract Z from A, we get the number of neutrons. When we subtract the atomic number from the mass number. Now, once again, chemical reactions, we have a rearrangement of the atoms. They don't change in identity. And that's why when we balance chemical equations, we say that we must have the same number of atoms of each element before the reaction and after the reaction. The nature of the elements do not change in chemical reactions. For nuclear reactions, the identity of the element changes. And it happens through what we call radioactive decay. Decay or decomposition would be the reaction of the nucleus of an atom. This is sort of a separate subfield of chemistry. And just like it happens with language, that we may use different words in the East Coast to describe the same objects than the words we would use in the West Coast. So in science, oftentimes, depending from which discipline you approach a topic, we use different terminology and different symbols. A lot of the things that we do in nuclear reactions probably, I would say, come more from physics and from chemistry. But nuclear reactions are chemistry because we're studying the change in matter. But at any point, it is important to understand this new symbolic language and the terminology. We have here 6 or 7 different particles, actually 6, because we gave the same thing 2 different names here for the electron and the beta particles. They are the same equivalent, but we use 2 different names depending on what's happening. So we have the particles, we have the symbols that we've used before, and we have the nuclear symbols. So for instance, the proton, so far we've described it using P+. In nuclear chemistry, we're going to describe it as the nucleus of the hydrogen atom, and it will be described by the letter that represents the symbol of the element and the number of protons and number of neutrons. So the number of protons would be the atomic number, in this case 1, and the number of protons would be given by the difference between the mass number and the atomic number. In this case, the number of neutrons is 0 because the atomic mass is 1 and the atomic number is 1. So we can represent it using the H, or we can represent it using a P. And we show atomic mass and atomic number. Now, this H here does not represent the atom, because for nuclear reactions, we don't worry about the electrons. We disregard the electrons. They are there, but they are not participating in the chemical transformation. So the H will symbolize only the nucleus. For the neutron, we have N, and again we have the atomic number that would correspond to a neutron. Neutron doesn't have an atomic number, so it would be 0, and the atomic mass would be 1. For the electron, we have E. The mass is negligible, so we have 0. And for the atomic number, we have a -1. And we're going to think of it, at least for now, as just being the opposite of a proton. The proton would be +1 up here, so the electron will be -1. The alpha particle has 2 protons and 2 neutrons, which makes a mass, will give you a mass of atomic mass of 4. And the species in the periodic table that has 2 protons and 2 neutrons is helium. So when we talk about an alpha particle, we can represent it as an alpha, or we can represent as He, the chemical symbol for helium, understanding again that we're not representing the atom, but we're representing just the nucleus of helium. And it may be a little bit easier to see when we're writing the nuclear equations if we use He, the atomic symbol. The beta particle again will be the same as the electron. We call it a beta particle when it is being released, and we call that a beta decay. And we talk about the electron capture when the nucleus adds one electron. So it is the same particle, but we just use different names in different situations. And the positron would be the same thing as a beta particle, that is as an electron, but with a positive charge, or positive a +1 atomic number. And again, the mass is 0 because it has the same properties of the electron, except for the charge or the atomic mass. The atomic number. Good, so now we know something about the nucleus. This is just a review from Chemistry 1A. We call the isotopes in nuclear chemistry, we call them different names, and most often we call them nuclides. And there are about over 2,000 nuclides that we know of, and approximately 90% of them are radioactive, so we refer to them as radionuclides. And we identify the nuclides or isotopes by the mass number. So we say uranium-238, uranium-235. We understand this is the atomic mass. And I know all of you have already memorized the atomic numbers for all of the 118 elements on the periodic table. So you know uranium would be 92. Another way we have to represent nuclides is by showing the atomic mass as a superscript to the left and the atomic number as a subscript to the left of the atomic symbol. And again, the electrons are not relevant for nuclear chemistry because they do not participate in the chemical transformation. Here we have two more examples, neon 21, neon 20. They have the same number of protons because it's the same element, neon, but evidently they have different number of neutrons because they have different atomic masses. We have the other way of representing them here, and this introduces the concept of nucleon. Nucleon is a word that we use to describe both the proton and the neutron in the nucleus. So this first one here has 21 nucleons, combining the protons and neutrons, and this one here has 20 nucleons. They're isotopes. We're going to stop here and continue in the next video.